Now, let us discuss this bias circuit with emitter resistor, and this is basically the modified form of fixed bias circuit, uh, in which a resistor is basically connected to the emitter junction. So this circuit, let us draw this circuit first and then analyze and see the stabilization by virtue of this arrangement. So what we do in this case, let us assume that we have an NPN transistor, and here we have the load resistance. We have the common potential here. Uh, Say this is plus VCC. All right, so that the input circuit is reverse biased. This is RB. Let us join it like this. So this is my RB, and here what we do, this is an NPN transistor. So here we introduce an emitter resistance, so that is RE, and then we'd like to have have a common line of ground, and then here we will have the output. Say here we have a capacitor, say C1, and this is my VCE, and this is my VI. So here we have this as RC. Here we will have the collector current IC. Here we will have the emitter current IE, and we can make use of a bypass filter here, so as to say this is C2, and we can have a capacitor over here to block DC. So this will be my, let me have this as the VI here. Okay, now we want to analyze this circuit and see the impact of the modifications that we have done to the fixed bias circuit. All we have done is we have introduced an emitter resistance here. Now we have the input circuit, and we would like to apply KVL. So applying KVL to the input circuit, right? So we will start from VCC. So we can write VCC is it is IB. Here we will have the IB. So this is IBRB plus this VBE. So this will come up as VBE plus IERE. There's no confusion about it, as simple as anything. And from this equation, we want to calculate this IB. So this IB will come out to be VCC minus IERE divided by RB, right? And there is one more term missing, that is this VB E, so must be subtracted here, VBE. And as we understand from the previous lecture on fixed bias, this VBE for germanium or silicon, it's very less than that of VCC. So we can avoid this VBE, and we can have the expression for the base current. So clearly we can see here that the base current has a dependence here. This is VCC minus IC RC divided by RB. All right, so till now it's fine, it's going fine. So now Now let's analyze this thing that what's going on. So let's take an account of temperature. Okay. So what sort of change temperature can bring in the system? So so what should I say here is that suppose the temperature increases, right? So if the temperature increases, this will certainly increase the leakage current, which will certainly increase the collector current, right? As well as the emitter current. So there will be rise in collector current, and there will be rise in emitter current, and this will result in voltage drop across this emitter resistance, right? So this drop will also increase. Uh, and certainly this will reduce the base current IB. The base current IB will be reduced. So this in turn will reduce the collector current. So when there is drop proportional, that will reduce IB, and that in turn will reduce IC to its original value. Thus the operating point is stabilized by the circuit. Must be clear. Now, the next important point is right. Suppose if we replace this transistor by another transistor of same number, same preparation, same kind of transistor, and let us assume that the beta for the new new transistor that has been used is more than that of the previous one, which was originally used in the circuit. Now, under those circumstances, what's going to happen? The increase of beta, what increase of beta will do basically, it will increase the collector current, right? It will increase the collector current, and proportionally the emitter current will increase. This will increase the drop IERE, and thus decrease the base current at the same time. This in turn will reduce the collector current to its original value, and thus stabilizes it stabilizes the operating point, or what we should call Q point of this configuration. Now, if we go on from here, if we move on from here in terms of external, we would like to apply KVL in the output circuit. So what we are going to have in the output circuit. Okay, so we are going to have here VCC. Okay, this will be equal to IB or B. Now VCC is, oh sorry, this is where am I right now? Yeah, here is. So we are using KVL in the output circuit here, and we will start from this plus VCC, and we will end here in terms of IERE. So what we are going to write here is we will have ICRC. So this is wrong here. So this is VCC, then IC. This is VCC, then ICRC. So this is ICRC, and plus we have VCE, and plus it will finally end here. It will be IERE. So we have applied the KVL in the output circuit. In this case, and so moving on from here, now beta, now since beta is very large, and we can approximate this emitter current to the collector current, right? So if I go with another step, this VCC, this VCC is, I would like to get this VCE from this equation, because this is another coordinate of the Q point. So VCE will be VCC minus ICRC, then minus IERE. This should be the case, right? And here I think here we can use the equation that IE is IB plus IC, right? We can use this equation here. So if I substitute this equation here, in this equation, I'll get VCE is it is it is VCC minus IC or C, then minus, instead of this IE, I would like to write IB plus IC times RE. Okay, so we have some common terms. So this VCE will be VCC, then minus IC times, so this is RC, okay, plus, sorry, this is RC plus RE, right? Then minus IB RE. So we are here, and we have VCE equal to VCC minus IC times RC plus RE minus IB times RE. So if we go back, to the equation, and to the equation of stability, the stabilization equation that we have, what's that? We have the stabilization equation as, if S stands for stabilization, that stabilization is 1 plus beta by 1 minus beta times delta IB by delta IC. Now, my aim basically is to find out this stabilization for this particular configuration. I want to go with that. Now, so if I come back here in this equation, I can have if I go with this equation, that VCE is VCC minus IC times RC plus RE minus IB RE. I would like to differentiate this equation with respect to IC. If I do that, and I can use here, instead of RC, here I have IC and here I have IB. So if I differentiate this equation, I'll have 0, then I'll have 0, then I'll have, because I am differentiating it with respect to IC, here I will have RC plus RE, then minus delta IB by delta IC RE. Now this should be the case. So from here I can have delta IB by delta IC equal to RC plus RE divided by RE. So the variation of base current with respect to the collector current. So here, instead of this, we can have the stability factor, that's 1 plus beta by 1 minus beta times RC plus RE divided by RE. And we can see here this this RC plus RE by RE. From this equation, what we observe is that the stability factor will come out to be less than that of 1 plus beta, right? So now if this stability factor is less than 1 plus beta, this is certainly going to improvise. This is certainly going to improve the situation in terms of fluctuations. And at the same time, this equation can be transferred in terms of the RB. We can have the transformations like IC by IB equal to beta, and we can use the equation IE equals to beta plus 1 times IB. So we can translate down this equation into some final equation, and that final equation would be, this stability factor would be 1 plus beta times RB plus RE divided by RB plus 1 plus beta RE. Now again, we are trying to have the same interaction here. That is the stability factor. This will be less than that of 1 plus beta. Now why it will be less? For that, this RB has to be small, and this RE, the emitter resistance, has to be extremely large. So when these two conditions are met, the stability factor that's linked with this circuit will come out to be less than 1 plus beta, and that's going to fix that's going to fix the Q point of the given circuit.